Welcome to the Deep Dive, the show where we turn complex research into crystal clear knowledge just for you.
Yeah.
Pick up your phone, maybe look at your computer monitor, or just picture an electric vehicle, accelerating totally silently. What actually connects all these incredible leaps in technology?
It's something most people never see.
Exactly. Today, we are diving deep into the 17 chemical elements responsible for, well, pretty much this entire modern miracle, the rare earth elements.
That's absolutely right. These elements, we're talking neodymium, europium, cerium, and their 14 siblings on the periodic table, they are the unseen foundation of our digital age.
Unseen but critical.
Totally. If these 17 elements just vanished from the global supply chain, well, you'd lose about 45% of all magnet production.
Wow.
Our green energy transition, it would grind to a halt, and most high-tech electronics would simply stop working. They're basically irreplaceable in how we design things now.
We've got this huge stack of sources here. Really comprehensive stuff covering everything from their unique atomic structure, their properties, all the way to the complex geopolitics and even new research trying to replace them.
Yeah, a lot to cover.
So our mission is clear. We need to unpack what gives these rare metals such indispensable, almost like technical superpowers, and why securing their very concentrated supply chain is, well, maybe the biggest strategic challenge facing industrial nations today.
And what's being done about it? The innovation side.
Exactly. What innovations are desperately trying to solve that big problem?
Okay, let's get into it. To really understand why they're so valuable, we have to start super small.
Like atomic level small?
Yep, their unique atomic architecture. Because that's where the magic, truly begins.
Okay, so we're talking electrons, specifically these things called 4f electrons. Now, most elements, they work with their outer electrons, right? The valence shells.
That's usually the case, yeah.
So what makes this deep internal layer of 4f electrons the absolute key to the rare earth magic?
Well, what's fascinating here is how these 4f electrons are sort of tucked away inside the atom.
Tucked away.
Yeah, they occupy this internal orbital zone, and they're shielded quite significantly by the outer valence electrons. Shielded from the external environment, from chemical bonding.
Okay.
You can almost think of it like a tiny, dense fortress deep inside the atom. And this shielding lets these electrons keep their unique quantum characteristics without much interference.
Ah, so they're protected in a way.
Exactly. And this internal shielding is the source of pretty much all their amazing properties. It allows for extremely stable and powerful magnetic anisotropy.
Which is key for magnets, right?
Crucial. And also incredibly precise light emission that's luminescence and controllable oxidation states for catalysis.
Oh.
Things other materials just can't replicate easily. That's why they're so hard to substitute.
That atomic detail, that shielding.
Yeah.
That's what really sets them apart.
No.
So, okay, let's translate that. Where do we see this specific atomic power having the biggest impact in the real world?
The single biggest application, no contest, is permanent magnets. It consumes nearly half of all global RE output.
Almost half. Just for magnets.
Just for magnets.
Wow.
Neodymium, Nd, praseodymium, Pr, samarium, and dysprosium, those are the real workhorses here.
And the famous one is the neodymium magnet.
That's the one. The combination of neodymium, iron, and boron, the NdFeB magnet. It is, quite simply, the strongest type of permanent magnet available anywhere on Earth.
And that strength comes directly from those 4f electrons.
It's a direct consequence, yeah. Those shielded 4f electrons coordinate. They help align the magnetic fields of metals like iron in this highly directional, really stable way.
So it's like they're marshaling the magnetic forces.
That's a good way to put it. And this level of intrinsic magnetic stability gives them their immense power-to-weight ratio.
And that ratio is, well, it's pretty staggering. I saw in the research an NdFeB magnet can store up to 18 times more magnetic energy than a traditional iron magnet of the exact same size.
18 times. Think about that.
That's the difference between, say, efficiently powering a massive offshore wind turbine or fitting a high-performance electric motor under the hood of your car instead of needing, a huge, heavy lump of iron.
Exactly. Miniaturization, efficiency, high power, it all stems from those shielded 4f electrons.
Incredible.
And it's not just magnetism. Look at cerium, C. It's a fantastic catalyst.
Why is that?
Because it has this ability to reliably switch between its oxidation states, C, and Sakura. It flips back and forth controllably.
Okay.
And that reliable switching makes it super effective at speeding up chemical reactions, particularly the ones related to pollution control in cars.
Right, catalytic converters. And what about the screens we're all staring at? You mentioned luminescence.
Yeah, if you're watching, say, the latest Marvel movie on a really nice 4K screen, you definitely have electrons to thank for that visual pop.
How so?
Elements like europium for the reds and terbium, TB for the greens, they use this electron light emission process to give off very specific wavelengths of light very efficiently.
So that gives us the vivid colors and the brightness we see in modern LEDs and LCDs.
Precisely. Sharp, bright, efficient color.
Okay, so the science is fascinating. Now let's zoom out a bit. The sources highlight 5 foundational sectors where these REs aren't just useful, they're essential.
Foundational is the right word. They underpin huge chunks of the modern global economy. Number one, as we mentioned, is permanent magnets. Over 45% of global REE demand.
And these are absolutely critical for green energy, right?
Non-negotiable, really. Take a big, direct drive wind turbine generator. A single one can contain hundreds of kilograms of NdFeB magnets.
Hundreds. In one turbine.
Yep. They are literally turning wind into usable electricity all over the world. And of course, EV motors, too.
What's number 2?
Catalysts. That accounts for about 16% of demand. We mentioned cerium already.
For the catalytic converters in cars.
Exactly. Essential for cutting down smog, meeting emission standards worldwide, but don't forget fossil fuels either.
How are they used there?
Lanthanum and cerium are vital for stabilizing certain catalysts, zeolite-based ones used in fluid catalytic cracking, or FCC in petroleum refining.
So making gasoline and diesel.
Yeah, you couldn't make modern fuels as efficiently without them.
Okay, number 3. Sounds like it's electronics.
Electronics and displays, yep. Beyond the europium and terbium giving us those colors and phosphors, we also rely heavily on lanthanum.
What does lanthanum do here?
Lanthanum-based glass has a really high refractive index and low dispersion. Fancy terms meaning it bends light very effectively without splitting it into colors too much.
Ah, so perfect for camera lenses.
Exactly. High-end professional camera lenses, specialized optical fibers. That clarity comes from lanthanum glass.
Number 4 must be batteries then.
Battery alloys and energy storage. You got it. Lanthanum, again, is a major component in the anodes of nickel metal hydride, or NiMH, batteries.
NiMH, those are big in hybrids, right?
Still are in many. And here's a stat that shows the scale. One source noted a single standard hybrid car might need 10 to 15 kilograms of lanthanum just for its battery pack.
10 to 15 kilos per car. That's a lot of lanthanum.
It adds up very quickly when you think about millions of vehicles.
Okay, and finally, number 5. This one really highlights the strategic angle.
For sure. Aerospace, defense, and specialized technologies. This sector depends heavily on a different kind of RE magnet. Samarium cobalt, or SEMCO.
Why SEMCO and not the neodymium ones?
Heat resistance. Unlike NdFeB magnets, SEMCO magnets keep their powerful magnetic properties up to a pretty staggering 350 degrees Celsius.
350 C, that's really hot.
Extremely hot. And that stability is absolutely critical for things like actuators and fighter jets, advanced aircraft engines.
Things that get very hot under stress.
Exactly. And also essential components in precision-guided munitions. You need reliability under extreme conditions there. Lasers, too.
So, okay. If we connect all these high-tech, critical applications, it really paints a picture of vulnerability, doesn't it?
A massive, concentrated, strategic vulnerability. That's the unavoidable conclusion.
Yeah. REEs are clearly the backbone of the modern economy, our defense, our green transition, yet the supply chain is anything but diverse or secure. The geopolitics here feel as dense as the elements themselves.
They really are. The sources are pretty clear on the numbers. In 2024, global RE production was around 390,000 metric tons.
Okay, and the concentration?
China accounted for roughly 69% of that global output, about 270,000 tons.
69%. Just let that sink in. Who's next?
The next largest producer globally is the United States, but way behind it, only about 11.6%. Then you have smaller amounts from places like Myanmar, Australia, Nigeria.
That gap between number 1 and number 2 isn't just wide, it feels like an industrial chasm.
It is. And China also holds nearly half of the known global reserves of these elements, so the dominance isn't just in current production, it's in future potential too.
Which creates this powerful economic and, frankly, strategic lever. Any disruption over there, whether it's accidental or, political, it immediately hits a global production of EVs, wind turbines, defense tech, everywhere.
And this brings us back to something we touched on earlier. Why is it so incredibly difficult and honestly messy to separate these elements, even if you find a mine outside China?
Right, you mentioned the lanthanide contraction.
Exactly. It's a consequence of that atomic fortress, those 4 electrons we talked about.
Walk us through that again, but maybe focus on why it makes separation so costly and energy intensive.
Okay. So because those 4 electrons don't shield the nuclear charge very well as you move across the series, the atoms actually shrink slightly.
The lanthanide contracts.
Right. The ionic radius decreases steadily across the whole lanthanide series. The practical result is that the chemical properties of adjacent elements, like, say, neodymium right next to praseodymium, are virtually identical. They behave almost exactly the same way chemically.
Like chemical twins, almost.
Very close twins. So when you try to separate them using the standard industrial method, which is called solvent extraction,
Okay.
the difference in how they dissolve or partition between 2 liquids, we call that the separation factor. It's minuscule, often only between 1.01 and 2.26.
1.01. That's
Yeah.
barely different at all.
It's tiny. So to get the high purity rare earth oxides you need for magnets or phosphors, you need these massive, complex industrial facilities. They run the material through hundreds, sometimes thousands of cascading stages of extraction and refinement.
Thousands of steps just to separate 2 elements.
For high purity, yes. It's an exhausting, incredibly energy-intensive process. And worse, it generates enormous amounts of acidic and sometimes radioactive waste.
Okay, so if the difference is that tiny a factor of maybe 1.01, it sounds like the industry is just fundamentally stuck with this super complex, polluting, high-energy method. Is that the case?
Well, that has been the reality for decades, yeah.
Mhm.
But the good news is that this huge strategic challenge, this bottleneck, is fueling some really intense innovation all over the world.
People are trying to find better ways.
Desperately. The economic and strategic need for cleaner, more secure, more diverse supply chains is driving some incredible scientific breakthroughs, both in processing the ores and in finding substitutes.
Okay, let's talk processing first. We need greener, faster ways to pry apart those chemical twins. What were some key breakthroughs the sources highlighted?
Okay, 3 big ones stood out. First, there's bioleaching.
Bioleaching, using biology.
Exactly. Researchers are basically harnessing the power of microorganisms, specifically acid-loving bacteria, acidophiles, to selectively leach REEs out of their ores or waste materials.
How does that help?
The big advantage is that it operates at ambient, normal temperatures and pressures. So it dramatically reduces the need for the brutal heat and toxic chemicals used in traditional acid leaching.
That sounds much greener.
Much greener, and they're getting better at it. The sources mentioned systems biology approaches achieving up to a 73% improvement in extraction efficiency compared to older methods. That's a huge step for sustainability.
So, using tiny natural machines to do the heavy lifting. Okay, what about recycling? We must have tons of these elements already in old electronics and magnets.
Absolutely. And that's where electrochemistry is making strides. The Pacific Northwest National Laboratory, PNL.
PNNL, okay.
They developed a selective room temperature electrochemical processing method.
Room temperature.
Yep. It allows them to recover specific REEs directly from complex alloys, like used ND-Feb magnets, without using harsh chemicals or needing extreme heat.
That sounds vital for creating a circular economy, right?
Yeah.
Getting these valuable materials back.
Precisely. Closing the loop instead of just constantly mining more.
Okay. And the third breakthrough, you said it tackles that agonizingly small separation factor problem.
Yeah, this one's really clever. Advanced membrane systems.
Huh?
Researchers, I think it was at the University of Texas at Austin.
Okay.
They've engineered these artificial membrane channels. Think of them like highly selective filters at the nanoscale. And they can achieve concentration factors over 800 times higher than traditional liquid extraction, especially for the valuable middle REs.
800 times more efficient.
Yeah. Imagine, if you can make the separation 800 times more efficient at each step, you might reduce those thousands of stages down to something far more manageable, quicker, and cheaper.
That really could be a game changer. Yeah. Makes new mining projects outside of the current dominant player potentially much more viable.
Exactly. It lowers the barrier significantly.
What if we just skipped eating REEs altogether? At least for some things.
Yeah.
The sources mentioned a real push to develop rare earth-free magnets, which is where almost half the demand is.
Absolutely. That's a huge area of research, especially in material science labs, focusing on elements that are, abundant and cheap.
Like what?
The main contender right now seems to be iron nitride. FN.
Iron nitride, just
Right.
iron and nitrogen.
Yep, uses super common, earth-abundant iron and nitrogen. And it shows magnetic properties that are actually comparable to some of the lower-grade RE magnets. There are companies like Niron Magnetics actively working now to commercialize FN for things like motors and sensors.
Okay, that sounds promising.
Uh,
And then there was my favorite discovery you mentioned,
mm.
something straight out of astrophysics.
Yes. That would be the synthesis of tetratonite.
Tetratonite.
Uh,
Sounds like something from Marvel.
It kind of does. It's an iron-nickel alloy, Fenny. And it naturally forms incredibly slowly, only over cosmic timescales like billions of years inside certain types of meteorites as they cool.
So it's a space magnet.
Pretty much, and it possesses extremely strong magnetic properties, naturally. The breakthrough is that researchers are now figuring out ways to synthesize it in the lab relatively quickly.
So speeding up a billion-year cosmic process down to weeks or something.
Essentially, yeah, it represents a potential pathway to getting high-performance magnets using only common Earth-abundant metals like iron and nickel. No rare earths needed.
That's just, wow, true material science wizardry. Almost like Star-Lord pulling a magnet out of his chest, but, made on Earth.
Something like that shows the ingenuity being applied to this challenge.
Okay, we have covered so much ground here. From the deep atomic foundations through the critical applications, the sharp edge of the geopolitics, and right up to the cutting edge of innovation. It's crystal clear how indispensable these 17 elements really are.
It really is. Maybe we can boil it down to 3 critical takeaways for you from this deep dive.
Let's do it.
Okay, first, the invisible engine. Rare earth elements, powered by that unique shielded 4F electron structure, they aren't just advanced materials, they are fundamental enablers of modern society.
Enabling everything from EV motors to bright phone screens to defense tech.
Exactly. They're irreplaceable in many current designs. Second takeaway, the supply constraint.
Big one.
Yeah, the global supply chain is dangerously concentrated, with one country, China, producing about 69% of the world's supply. This creates a critical geopolitical and strategic risk that just demands urgent diversification.
It's a vulnerability we can't ignore.
We really can't. And third takeaway, the innovation imperative.
The response to that vulnerability.
Right. That strategic challenge is driving incredibly rapid scientific progress. We're seeing innovations like bioleaching, new electrochemical recycling, advanced membrane separation.
And the development of those rare earth-free alternatives like iron nitride and that amazing synthesized tetratonite.
Exactly. These are all emerging rapidly to try and secure a more sustainable, more secure, and more decentralized global supply for the future.
It's truly amazing. These elements really are the unsung heroes and maybe the Achilles heel defining our century. They're why modern tech works, and they're why nations are now in this huge race to diversify supply and revolutionize how we get them.
Couldn't have said it better.
Now, for a final provocative thought to leave you with. Considering how absolutely essential these 17 elements are for the green energy transition for wind turbines, for EVs, and given the massive environmental footprint of extracting and separating them the traditional way, how will global policymakers, how will we balance the urgent need for strategic supply security against the equally urgent moral and ecological demand for environmental sustainability, especially as the world races towards a fully electrified future?
That is the multi-trillion-dollar question, isn't it?
It really is. That's the puzzle facing the next generation.
Yeah.
Something to definitely mull over.